Here are the answers to Pythagorean theorem converse. Now, just FYI, the converse problems didn't start until number 23. So if you didn't get to that and you didn't get to number 23, then you did zero practice over Friday's lesson. So just be careful. The 1 through 22 was awesome radical practice. It was awesome Pythagorean theorem practice. Both of those will be on your quiz tomorrow, but none of those were converse practice. So make sure you've tried 23 through 31. All right, taking a look at number 5 from the Pythagorean theorem converse homework. We know that this is a right triangle. So, let's see. There we go. So when we have a right triangle, we know that we can apply the Pythagorean theorem to the side lengths. So what do we have here? X squared plus 4 squared is 16. Square root of 3 squared is 3. So we're doing good so far. We need to move that to the other side. 64 minus 16 times 3. Oh, it's 16. X squared equals 16. X is good old 4. Number 11. A television screen measures 15.5 inches high and 19.5 inches wide. A television is advertised. Have you ever went to look at TVs to buy one? When it says it's a 20-inch TV or a 32-inch TV, they're not talking about the width. They're not talking about the height. A TV is advertised based off of its diagonal. So what's the approximate length of the diagonal of the screen? That way we know what size screen it is as the advertisement in the store. So we're literally just doing a squared plus b squared, except we don't have to do any factor trees because it's a real world problem and we get to just use decimals. So 15 squared plus 19.5 squared. And we take the square root. We get, by the way, 620.5. Oops. There we go. Equals x squared. So we take the square root of 620.5 and we get, it's about a 24.9, but I rounded it to a 25-inch TV because they probably wouldn't advertise it as a 24.9-inch TV since this is a real-world problem. Okay? Ooh, 15's a good one. It's got some x's in it. Here we go. 15. A squared plus b squared equals c squared. And once again, I bet that you're asking about this because you might have forgotten to put parentheses around the 3x. You have to square the entire side, not just part of the side. So that's saying x squared plus 9x squared equals, I'm not even going to square 40. All right, so what do we have? 10x squared equals 40 squared. Divide by 10, divide by 10. So in my calculator, I'm doing 40 squared divided by 10. And I'm getting 160. So x squared equals 160. We need to square root both sides, and that's 4 root 10. Yep. So number 20, you're going to see a lot more when we get to the area and perimeter unit, but why not expose you to it now as well? All right, sorry, number 20. So we want to find the perimeter. You already know what perimeter means. It's an isosceles trapezoid, so tick mark, tick mark. The base is 10. Oh, no, this base is 10. The other base is 18, and the height is 8. And we want to find the perimeter. So the only thing we're missing to add up all the sides are those legs, the congruent sides. So I'm going to call it x. This is what we need. They're both x because they're the same. Now what I'm going to do is I know that this 10 is congruent to this 10. So if I did 18 minus 10, I would have 8 left, and I'm going to want to divide that by 2 and have a 4 and a 4 here. So now I'm going to look at this triangle right here, drop my pen. I'm going to do Pythagorean theorem with this triangle right here. A squared plus b squared equals c squared. So I'm doing 4 squared plus 8 squared, and I'm getting 80. So then I need to factor tree the 80. 4 root 5. Okay. So, I know that this is 4 root 5. 4 radical 5. So now I just need to add up all the sides. We know that to add and subtract radicals, they have to be like terms. So let's add up all the like terms. I can add the 10 and I can add the 18. I'm allowed to because they're like terms. So 28. And then I can add the 4 root 5 and I can add the 4 root 5 because they're both root 5s. What's 4 plus 4? It's 8. So 28 plus 8 root 5. And you just did a problem from a future unit. You just traveled to the future. Congratulations. What do you think of when you hear the word mean? Not as in like Mean Girls mean, but like mathematical mean. Average, yeah. So if I asked you to find the mean of 8 and 10, what would you do? I mean, it'd be kind of silly. Maybe let's do 2 and 10. So you would probably tell me to add the numbers and divide by 2, I'm guessing is what you would immediately go to, right? So in your mind, in your schema, your prior knowledge, that is what you think of when you hear mean. You think average, you think add them up and divide by 2. But when you think of mean, you're actually thinking of an arithmetic mean. That's what you're thinking of, an arithmetic mean. And you probably didn't know that there were more means out there in the world. You probably thought arithmetic was the only type of mean there was. But that's what we're learning about today. So when you hear mean, the one you've been taught is add the numbers, divide by 2. But the one we're going to learn today is called a geometric mean. It's called a geometric mean. And we're going to learn how to do that. So title your notes, Geometric Mean. Yes, geometry is so special, it gets its own mean. That's right. You heard it. All right, go ahead and write down the definition. This is a good thing to have in your notes. What is a geometric mean? For any two positive numbers a and b, the geometric mean of a and b is the positive number x such that a divided by x equals x divided by b. So guys, does that look like what we did in the warm-up? Do y'all remember that? When we were finding the missing sides and we used similar triangles to find the missing sides and our proportion ended up looking kind of like this? So geometric mean must be somehow connected to similar triangles. So in geometry, in our class, we're going to use geometric mean and it's going to really only have an application to finding missing triangle side lengths. That's what we're doing here. But I kind of wanted you to know that other people in the real world use geometric mean for something totally unrelated to triangles at all. So I wanted to give an example because I thought this was a good application. You want to buy a new camera, okay? One camera has a zoom of 200 and you read the ratings online and it gets an 8 in ratings, okay? So people like it. But then you're looking at a nicer camera, a better camera. It has a zoom of 250, but it only got 6 stars in the reviews. So which camera is the better one to buy? You wouldn't, if you wanted to compare these, like apples to apples, if you wanted to compare them, you can't just add 8 plus 6 and divide by 2. You know what I mean? They're on different scales. They're different types of cameras. So instead of doing that, you find the geometric mean, which we're going to talk about in a minute. So you multiply the lens by the rating, and you take the square root. You multiply the lens by the rating, and you take the square root. And that's so much better than doing this to try to find how good the camera is. You wouldn't do 200 plus 8 divided by 2. That number wouldn't mean anything to you. But if you do the geometric mean of both of them, you get 40 and you get 38 plus 0.7. So actually, the camera with the less better zoom would be the better buy if all those ratings were really true. You know what I mean? Other fields that use it, if you read down there, banking uses it, investment banking, environmental systems. Other things like environmental systems that has to rate two companies on different things. It's rating on different scales. And so if there are different scales, then that means you can't just add and divide by 2. But the geometric mean will help you compare the numbers. All right, I just wanted you to know how it was used in the real world. All right, let's do an example. Find the geometric mean of the numbers 4 and 9. So the geometric mean, by definition, is the number x such that 4 divided by x equals x divided by 9. We would, of course, then cross multiply. 4 times 9 is 36. X times x is x squared. Then, of course, I made it a pretty number. We would take the square root of both sides. We would technically get plus or minus 6, but by definition, the geometric mean has to be positive because it's triangle side lengths we're talking about here. So anyways, that's why we only keep the 6. Now, another way to think of it is the geometric mean of 4 and 9 is the square root of 4 times 9. Because honestly, that's what you're doing. Look, square root of 36, square root of 4 times 9. So I just want to compare it. If I went back to this slide, I just want to compare it to what an arithmetic mean is. So when you find that, you add your numbers and you divide by 2. By geometric mean, you step up both of those. Instead of adding, what do? You multiply. I just stepped up adding to the next thing. Instead of dividing by 2, what can you do greater than dividing by 2? You square root. So it's like taking the arithmetic mean, but it's like stepping it up. If you had more than one number under there, which we never will, never in this class, but if you did have more than one number, it's pretty cool. If you had A times B times C, you would take the cube root because there's 3 numbers. And if you had 4 numbers under there, you'd take the 4th root, etc., etc. Alrighty. Do one more. Find the geometric mean of 10 and 40. Alright, guys. So technically, by definition, we would say 10 is to x as x is to 40. Whoops, sorry about that. We would cross multiply. X squared equals 400. And then we would square root both sides. X equals 20. Are you allowed to just use what I taught you earlier, though? Totally allowed. You are totally allowed to just say, I know the geometric mean is the square root of the product. Square root of the product. Product means multiply, and square root, you know what that means. So anyways, are you allowed to just go straight to that one? Sure. I'm totally okay with that as long as you know what you're doing. Alrighty. Here's just another FYI. We're not going to use this in this unit. I just kind of like you to know the background of things. The geometric mean of 2 numbers, like 4 and 9, is the length of one side of a square whose area is equal to the area of a rectangle with sides of lengths 4 and 9. Do you kind of understand what that's saying? So, what's the area of this square? 9 times 4, length times width, 36. What square out there in the world would have side lengths to where that would make its area also 36? These areas need to match, and then the side length would be 6. So 6 is the geometric mean of 4 and 9. That's kind of cool. I think it's cool. Okay. All right, we're going to skip around a little bit. We already did this in the warm-up, so I'm not going to go into this. But a geometric mean comes from the fact that these 3 triangles, little bitty triangle number 1, medium triangle number 2, and large triangle number 3, it comes from the fact that they're similar. We already showed that in the warm-up. We lined up the sides. We know which ones are similar, and that's why we're allowed to set up these proportions. So I'm kind of skipping through that part of this. When you draw an altitude, the altitude to the hypotenuse of a right triangle, it divides the triangle into 2 triangles that are similar to each other and similar to the original. You do not need to write this down. We did this in the warm-up, like I said. So today's focus is solving problems when 2 things happen. First, you have to have a right triangle. And second, you have to have the altitude drawn from the right angle to the hypotenuse. So if your picture doesn't look exactly like that, then don't use geometric mean to solve it. The picture has to fit those stipulations to be able to use what we're about to learn. All right. We already talked about this in the warm-up as well. We hit so many points in the warm-up. If triangles are similar, then their corresponding sides are proportional. So if their sides are proportional, we can set up a proportion. For example, AD is to BD, so first, second, as BD, third second is to CD. That is a geometric mean. See how the BD is repeated? It's like X and X. BD is the geometric mean of AD and CD. That's confusing. I get it. You should be confused. It's okay if you're confused. Let me show you in the picture what's going on. All right. AD is to BD as BD is to CD. Now, we're going to write a proportion that you can use on any problem anytime. Our proportion can't have letters in it like that because our triangle might not always be named the same thing. So we need to call these certain things and come up with our own proportion. Let's do the easiest one first. What is BD called in this triangle? What's BD called? But like vocab word. Good. Altitude. So I'm going to write the same proportion, but instead of BD, I'm going to call it the altitude because I can call that the altitude no matter what our triangle is named. Now is the hard part. We need to call AD something, and we need to call DC something. But we need it to work for any triangle we're ever going to use. Now keep in mind, AC is the hypotenuse of the large triangle. So AD is just a part of the hypotenuse, and DC is just a part of the hypotenuse. Now, does it matter which one we put first and which one we put last? Like if we said 4 is to x as x is to 9, will we still get the same thing if we said 9 is to x as x is to 4? Are those the same thing? When you cross multiply, will you get 6 every time? Yes, those are the same thing. So cool, it doesn't matter which one I put. So what I'm going to call these is I'm going to call AD, I'm going to call it hypotenuse part 1. Is that okay with you? And then DC, I'm going to call it hypotenuse part 2. So we're calling it part 1 and part 2. The hypotenuse got broken up into parts. So I'm just calling it part 1 and part 2. And it doesn't matter which one you put on top and which one you put on bottom. All right, go ahead and write that down in your notes. This is a shortcut to help you find the missing sides of a right triangle with the hypotenuse drawn. No, the altitude drawn. Write it down in your notes. Write that proportion down in your notes. All that stuff I said before was just background knowledge to get us to this one slide. This was our destination. So if you just ignored everything I said earlier and you just understand how this proportion works, then you'll be okay. But if you like to know where things come from, then it's good that I did all that talking. Okay, guys, let's do it. Ready? Here's a triangle. There's a missing side. I can't use Pythagorean theorem to find this side, right? It's the altitude of the triangle. I don't know how to find the altitude. But now that we know about geometric mean and similar triangles, we get to use our little proportion we made up. By the way, we just totally made that up. That little proportion on that screen, you won't find that in a textbook. You won't find that on Google. We just made it up so that we can use it every time. Okay? All right, so the proportion says hypotenuse part 1. You can pick any part. It doesn't matter which part you pick first. Then it says altitude, which is x. Then it says altitude, which is x again. He's making a double appearance. And then it says hypotenuse part 2, the part you didn't choose the first time. So 2 is to x as x is to 8. Cross multiply. Look how pretty that is. Once again, are you allowed to be presented this problem and literally just do this? Yes, you're allowed. But you have to understand when this is appropriate, when you're allowed to do this, and when it doesn't work. So once you've gotten to know the proportion well enough, if you just want to take the square root of the product, square root of 2 times 8, I'm totally okay with that. All right, there's one more proportion. Let's look at this one. Go ahead and write it down in your notes, and then we'll take a closer look at it. There's one more proportion because we might be looking for a leg. We might not be looking for the altitude or part of the hypotenuse. We might be looking for a leg, and we need to have a proportion to find it. Once again, All these proportions come from similar triangles. That's why we're allowed to do this. All right, so what is this saying? This is saying hypotenuse. Oh, so it's not a part. It's the whole hypotenuse, AC. Hypotenuse over a leg, and it depends on which leg you're looking for. In this one, it's BC. Equals leg, oh, so we're going to double use that leg, over, oh no, what does that mean? ADJSEG? It means adjacent segment. Remember, the hypotenuse got split into two parts. And I want to choose the part, DC, I want to choose the part that's adjacent to the leg I'm looking for. Here's the wonderful news. We are not going to make you memorize these proportions. We just want you to know how to use them. So if I project this on the board, if I give you this formula, I just need you to know how to apply it. Yay! All right, let's do it. Hypotenuse over leg. Okay, so what is the hypotenuse? Be careful, you're having to add these together. Hypotenuse is 18 over leg equals leg over adjacent segment. If this is my leg, which segment is adjacent, the 8 or the 10? Adjacent means next to. So you take the segment that's touching the leg you're looking for. I made it pretty again. What's the answer? I'm doing this for you guys. All right. Oh no, not a word problem. We only have 2 problems left, by the way, if you're having to leave. The altitude to the hypotenuse of a right triangle divides the hypotenuse into segments 3 centimeters and 27 centimeters long. Find the length of the altitude. You could draw a picture. You can orient your right triangle any way you feel like. I'm going to go ahead and put the right angle there and the altitude there. It divides the hypotenuse into segments that are 3 and 27. Find the length of the altitude. So which proportion are we going to use? The one we learned first or the one we learned second? We're not looking for a leg. We're looking for an altitude. So use the one, with the word altitude in it. So I know that that proportion says HP1, hypotenuse part 1, over the altitude equals the altitude over hypotenuse part 2. Easy as that. Man, I was just a pro of coming up with pretty answers, wasn't I? Nice. The answer is 9. Once again, I keep saying this, but could you have just read this problem and done this? If you knew what it was asking for and you knew there wasn't a leg involved, then yes, you could have just gone straight to your calculator, square root of 3 times 27. Yes, you could have. Last problem of the day. Oh my heavens, there's 3 variables. I'm going to let you think about it for a minute. Draw it in your notes if you have time. So on this example, I would recommend finding the easiest one first. And the easiest one to find is going to be y. Okay? Y is the altitude, and we're using that first formula, the first proportion. Hypotenuse part 1 over the altitude equals the altitude over hypotenuse. I keep doing my 3's weird. Hypotenuse part 2. So y squared equals 2 times 32. Y squared equals 64. Y is 8. Now here's the deal. Now that we have y, now that we know the altitude, you are more than welcome to use Pythagorean theorem. There's nothing wrong with finding x by doing a squared plus b squared. But since this is the geometric mean lesson, I want to keep doing geometric mean so we can practice a little bit more, okay? Let's find x using geometric mean. So to find x, we're going to use that other proportion. That other proportion says, take the hypotenuse. I had to add together to get that 32 plus 2. Hypotenuse over leg equals leg over adjacent segment. and the one that's adjacent to x is the 2. Hypotenuse over leg equals leg over adjacent seg. All right, 34 times 2, we're taking the square root of 68. So that's going to be 2 root 17. No decimals. Did you hear me, guys? No decimals, no decimals, no decimals, no decimals. It does say the nearest tenth. Never mind. Look at that. Someone in my first period gave me a decimal and I got mad at her. It says to the nearest tenth. I don't like that. You know what? Oh, I know why. It's because we used to teach geometric mean before radicals. Now we have radicals. And so now we can have exact answers. Oh, I feel so bad that I got mad at her. Oh my goodness. Well, I didn't really get mad. I just got Miss Tanton's version of mad, which is not really that mad. Okay, last one, Z. All right, so the formula, the proportion is hypotenuse over leg equals leg over adjacent seg. The one adjacent to Z is 32. You're just using the one you haven't used yet. 34 times 32, whoa, 1,088. 1,088. Let's see, factor tree that bad boy. I'm getting 8 root 17. Because it's 64 times 17, and 64 is a perfect square. Lesson over. Geometric mean worksheet for homework. Quiz tomorrow. The quiz is over simplifying radicals, Pythagorean theorem, and then there's a couple Pythagorean theorem converse ones. Only the ones where you're saying acute, obtuse, or right. None of the crazy ones. I just list the side lengths, and you just say which one it is. So the basic ones of Pythagorean theorem converse, not the scary ones. Have a great day.